For 152 years, a feature known as Black Diamond Pool in Yellowstone National Park was a place of quiet geothermal activity. Then, in 2024, that long silence was broken when it abruptly exploded. This year, in late April, it erupted twice more in under 24 hours, with the second blast proving more powerful than the first. Only 6 days later, and an ocean away, Hawaii's Kīlauea volcano unleashed episode 46 of its current eruption, sending a tower of molten rock 650 feet into the air for 9 consecutive hours. Both of these dramatic events are driven by the same type of geological engine deep within the Earth. This raises a profound question. What exactly is taking place beneath the surface of America right now? The story these two systems are telling is a genuinely unsettling one. If you find yourself already intrigued, we invite you to join us here at Calm Space, because this narrative is far from over. With one pool having detonated twice, and one volcano cycling on an 1-1-day clock, pressure continues to build in places we cannot see. Somewhere between the measured language of official monitoring and a series of events without a clear modern parallel, a gap in our understanding persists. Exploring that gap is what we are dedicated to, and you will want to be here as the next chapter unfolds. In a single week, the two most formidable volcanic engines buried beneath the United States both made their presence known, not with a whisper, but with a roar. And yet, the fact that they spoke at nearly the same time went largely unnoticed. On the 5th of May, 2026, the summit of Kilauea propelled a column of liquid rock 650 feet into the Hawaiian sky, a fountain of fire taller than a 6-story building. This eruption continued for 9 hours, generating an ash plume that climbed 20,000 feet into the atmosphere, high enough to disrupt commercial aviation and force pilots on trans-Pacific routes to alter their flight paths. By the time the fountain subsided back into the crater, an astonishing 6 million cubic yards of new basalt had been expelled from the volcano's throat. To visualize this, imagine enough molten material to fill the Empire State Building from its foundation to its spire nearly 5 times over. All in just 9 hours. It was a staggering display of planetary power. Now, hold that image of a brilliant orange tower erupting from the Pacific, because as this was happening, something far stranger was unfolding on the other side of the country, beneath a tranquil pine forest in northwestern Wyoming. It was an event that few news outlets took the time to properly explain. Just days before, on April 28th and 29th, a thermal feature named Black Diamond Pool, located within Yellowstone National Park, did something it hadn't done for 152 years. It exploded. Then, less than a day later, it exploded again. This second blast was even larger, hurling boulders bigger than baseballs across the pool's rim and shooting steam dozens of feet into the air. The force was enough to knock down nearby trees, with the impact zone just feet from boardwalks where tourists had walked the previous summer. On the surface, these two events could not look more different. One is a spectacle of fire, the other a violent burst of steam. One involves a glowing river of melted stone ascending toward the clouds, while the other is a sudden, forceful reorganization of the ground by superheated water. One is a phenomenon you can watch from a helicopter miles away. The other could happen without any warning if you were standing in the wrong place. But here is the critical detail that was lost in the headlines. Both the lava fountain and the steam explosion are surface expressions of the same underlying phenomenon. Geologists refer to this engine as a mantle plume, and it powers both of these incredible systems. A mantle plume is a narrow column of abnormally hot rock that rises from deep within our planet, possibly originating at the boundary between the molten outer core and the solid mantle itself. That boundary lies approximately 1,800 miles beneath our feet. These plumes are powerful enough to punch directly through the rigid tectonic plates that form Earth's crust. Where they break through, they create what are known as hotspots, volcanic regions that exist not at the edges of plates, where most volcanism occurs, but anomalously in their middle. This makes them strange, persistent, and a subject of intense scientific focus. There are only a handful of these confirmed mantle plumes on the entire planet. Iceland sits atop one, as does the island of Réunion and La Palma in the Canary Islands. The United States, however, is unique among all nations for having two of these rare and formidable deep earth engines located on its sovereign territory. And in the first week of May 2026, both of these systems sent a signal almost simultaneously that they were very much active. It is a coincidence of geological timing that is difficult to ignore. If you are like most people, hearing about such a coincidence immediately triggers a search for a connection. Our brains are wired to find patterns. When we observe two unusual events occurring so close together in time, we instinctively wonder if one caused the other. We look for a hidden mechanism, a deeper rhythm, or some form of synchronization beneath the surface noise. The timing feels meaningful, as if it carries a message. And this is where the story becomes more nuanced, for the truth is messier and, in many ways, more interesting than a simple pattern. These two systems, despite being powered by similar deep earth phenomena, are not directly connected. They are separated by thousands of miles, reside on different tectonic plates, and possess entirely different chemistries, plumbing systems, and geological histories. So while they acted up in the same week, one event did not cause the other. Yet, this timing is not meaningless. Buried inside this coincidence is a vital story about how one of these systems is behaving exactly as scientists expect, while the other is doing something that no one can completely explain. This is why this is not a disaster story, but rather a story about a profound gap in our understanding. It serves as a powerful reminder that we live on a planet whose interior we have only just begun to map. The most unsettling part of this narrative is not what is happening, but what we are not yet able to explain. Why did both of these ancient systems choose this moment to remind us they are still awake? Stay with us, because the answers lie in the details. Part 2. The problem of timing. To understand what is unfolding, we must lay out the timeline with precision, because the order of these events matters far more than the speed of the headlines. On the 28th of April, 2026, sometime during the late afternoon, Black Diamond Pool, located in the Biscuit Basin thermal area of Yellowstone, produced its first hydrothermal explosion of the week. Park geologists were on the scene within hours to begin their assessment. Following the initial hydrothermal blast, researchers carefully documented the aftermath. They mapped the radius of the damage, took thermal readings of the surrounding ground, and analyzed the pool itself. Its very structure had been transformed. The geometry of its floor was different, and the water's chemistry had shifted. By the metrics used to monitor Yellowstone, this was a notable occurrence, though not without precedent. The same pool had, after all, erupted just in 2024. So, while the event was certainly startling, it seemed to fit into an emerging, if very new, pattern. But this was only the beginning of the mystery. Less than 24 hours later, on April 29th, a second, more powerful explosion rocked the same pool. This rapid succession, with the second blast being larger, is the detail that has left scientists genuinely perplexed, a puzzle we will return to. Just 6 days later, on May 5th, Kilauea initiated its 46th episode of recent activity. For 9 hours, it produced sustained fountains of lava, reaching 650 feet, and sent a plume of ash and gas 20,000 feet into the sky. A dramatic display from one of Earth's most closely watched volcanoes, continuing a cycle that has been unfolding for the past 17 months. At the same time, these American systems were releasing tremendous energy. The global seismic record showed an unusual flurry of activity. On the very day Kīlauea was fountaining, A magnitude 5.8 earthquake struck along the Aleutian Arc off the Alaskan coast. This tremor was potent enough to prompt a tsunami advisory for some of the Aleutian Islands, an alert that kept emergency services on high alert for hours before it was eventually downgraded. Around the same time, the Philippines experienced a magnitude 5.5 earthquake, while the Kermadec subduction zone north of New Zealand registered a 5.6. On their own, none of these are considered catastrophic events. The planet generates earthquakes of magnitude 5 almost daily. Yet, the clustering of several significant tremors along the Pacific Rim, coinciding with two major hotspot events in the United States, is precisely the kind of pattern that ignites speculation. It naturally leads one to wonder if there is a hidden connection. This convergence of events raises an obvious question. Is some underlying force synchronizing all of this activity? Is the Pacific Ring of Fire pulsing in a coordinated rhythm? Or is this simply our minds doing what they are programmed to do, finding patterns where none exist? The truth is, entirely independent systems can align purely by chance. Statisticians have a term for this phenomenon, the clustering illusion. If you were to flip a perfectly fair coin 1,000 times, you would inevitably encounter streaks of 10 consecutive heads. These streaks might feel deeply significant, as if defying probability, but they are not. They are a natural and expected feature of randomness when observed over a long enough period. Our brains are simply wired to see meaning in such clusters. This same principle can be applied to seismic and volcanic activity on a planetary scale. Earth is a dynamic and noisy system where powerful events happen constantly. When 2 or 3 of these occurrences happen in close succession, our pattern-seeking instincts activate, compelling us to believe it must signify something more. And yet, even with an intellectual grasp of the clustering illusion, a nagging question often remains. Could there be a deeper form of synchronization at play? One that our current instruments are not yet sensitive enough to detect. We know that mantle convection cycles, which move vast quantities of material and energy through the planet's interior, operate on timescales of millions of years. However, our understanding of how these immense flows interact is far from complete. We do not know if subtle pressure waves can travel through the mantle in a way that simultaneously affects distant systems. In essence, we are confronted by the vastness of what we do not know. This uncertainty defines the central tension of our story. On American soil, we have 2 distinct hotspots, both reminding us of their latent power within the same week. The mainstream scientific explanation points to coincidence, a simple artifact of probability. In contrast, more fringe theories propose a grand synchronization. The most honest answer, the one scientists often give when pressed, lies somewhere in the middle. Shrouded in a fog of uncertainty about the true mechanics of the deep Earth, we will eventually explore the role of solar weather and the sun, as a separate hypothesis suggests something stranger is at work. But for the moment, it is crucial to hold on to the timeline. 2 active American hotspots, a global seismic backdrop that is unusually busy, and a public discourse that may be asking the wrong questions entirely. So, what is truly happening beneath the United States right now? And why does the answer seem to change depending on which volcano you are observing? If you opened nearly any news application during the first week of May, you would have encountered 2 profoundly different narratives about these events, both of them misleading in opposite ways. Yellowstone was given the doomsday treatment. Headlines warned that the supervolcano was waking up and that scientists were deeply concerned. It is a familiar rhythm. Whenever anything happens at Yellowstone, a certain type of headline writer defaults to the same script, because Yellowstone has become the boogeyman of American geology, the one system everyone has been conditioned to fear. So, when Black Diamond Pool exploded twice, the narrative wrote itself. the supervolcano is stirring. Kilauea, on the other hand, received the complete opposite treatment. The story struggled to even make national news. When it did appear, it was framed as a routine eruption, just another beautiful fountain of lava. The narrative suggested that Hawaiians are accustomed to it. Tourists were flocking to take pictures, and there was nothing unusual to see. But the truly wild part of this is that both of these media framings were fundamentally wrong. In fact, they were inverted. They had the entire danger profile flipped completely backwards. The reality of what was happening at each location was far more nuanced than the headlines suggested. Let us clarify this inversion. What occurred at Kilauea on May 5th was, in the most literal sense of the word, normal. It was the system operating exactly as it has been for nearly a year and a half. This was episode 46 inches, a sequence of 46 distinct events, and its behavior fell well within expected parameters. The geologists who dedicate their lives to studying Kilauea were not surprised or concerned. If anything, they were diligently taking notes on what is shaping up to be a remarkably consistent eruptive cycle. Hawaii's hotspot is functioning precisely the way it is known to function. What transpired at Yellowstone, however, is not normal. And this is not meant in the apocalyptic sense of a supervolcano awakening. The mainstream coverage actually got that part right. There is no evidence whatsoever of magma migrating toward the surface, nor are there signs of pressurization in the deep magma chamber. The ground is not deforming. The abnormality of the Yellowstone event lies elsewhere, in a more subtle and perplexing detail. Seismic monitoring networks are not detecting the kind of harmonic tremors that would signal an impending super-eruption. This is a crucial point, because it means the framing of this story as a global threat is incorrect. You can rest easy tonight. There is no planet-altering catastrophe unfolding. However, it is equally wrong to dismiss these events as merely routine. What transpired at Black Diamond Pool was anything but ordinary. For the second time in just 2 years, a geothermal feature that had been dormant for more than 150 years erupted violently. This time, it erupted twice within a 2-4-hour period, with the second blast being even larger than the first. This pattern of escalation and localized change within the system is the real story, and it is a detail that should not be overlooked simply because the deep magma chamber remains quiet. We must therefore learn to separate two distinct types of danger. First, there is the civilization-ending, global-scale risk that would require massive magma movement and a full caldera eruption. This is not what is occurring at Yellowstone. Then, there is the immediate, localized, and lethal danger, the kind where an individual happens to be in the wrong place at the wrong moment when a hydrothermal explosion hurls boulders into the air. This second type of danger is precisely what is happening at Yellowstone, and the evidence suggests it may be growing more frequent. This highlights the critical difference between a magmatic event, which is driven by molten rock, and a hydrothermal event, which is driven by water. Hydrothermal explosions are not fueled by magma breaching the surface. Instead, they are powered by water that has been superheated under immense pressure and is then suddenly released, expanding with incredible force as it flashes into steam. The consequences of such an event are entirely local. They pose no threat to the planet or even the broader region, but they are absolutely deadly to anyone within a few hundred feet. Here, we arrive at a fascinating inversion of expectations. In Hawaii, the loud and fiery spectacle is a system we largely understand. In Yellowstone, the quiet, anomalous event is the system that remains enigmatic. The detail that should truly capture our attention is not the dramatic fountain of fire, but the pool of water that erupted twice when it should have erupted only once. The real narrative is being missed because it does not conform to the dramatic script the public has been conditioned to anticipate. The quiet anomaly, it turns out, matters more than the loud eruption. To understand why, We need to explore what these two vastly different systems have in common, deep beneath the surface, because for all their divergent behaviors, they are running on the same kind of geological engine. Part 4. Two systems, one origin. Let us journey downward, far past the boardwalks and lava fountains, beyond the surface geology, through the crust, and past the upper mantle. We are heading for the source. In both Hawaii and Yellowstone, that source is what geophysicists refer to as a mantle plume. Mantle plumes are a peculiar and powerful force in geology. Most of the planet's volcanism occurs at the boundaries of tectonic plates, where one plate slides beneath another, or where two plates are pulling apart. The Pacific Ring of Fire, that famous arc of volcanoes encircling the Pacific Ocean, is composed almost entirely of this type of plate boundary volcanism. The Andes, the Cascades, Indonesia, and Japan all sit at the edges of plates, where the geometry of tectonic motion creates predictable conditions for rock to melt. A mantle plume, however, does not abide by these rules. It is a column of abnormally hot rock that ascends from deep within the mantle. When this column reaches the underside of a tectonic plate, it can effectively burn a hole straight through it from below. It requires no plate boundary. It simply rises, and where it rises, volcanism is born. This is the reason Hawaii exists in the middle of the Pacific Plate, thousands of miles from any boundary, yet hosts some of the most active volcanoes on Earth. The plate is in motion, but the plume beneath it remains stationary, continuously punching through the crust. It is at this point that the two American plumes begin to reveal their profound differences, despite their shared origin. The Hawaiian plume is situated beneath oceanic crust, which is thin, dense, and primarily basaltic in composition. As the plume melts the rock above it, the resulting magma is also basaltic. Basaltic magma has a low silica content, which makes it relatively fluid. It flows and fountains, moving like a thick syrup rather than a sticky paste. This specific chemistry is what allows Kilauea to produce the iconic rivers of red lava seen in countless documentaries. The magma's composition enables it to flow freely. The Yellowstone plume, by contrast, sits beneath continental crust. The North American continental crust is significantly thicker, older, and chemically far more complex than its oceanic counterpart. It is rich in silicates, granites, and the kinds of lighter, intricate rocks that form the continents. When the Yellowstone plume rises and melts this overlying rock, the resulting magma absorbs all of that silica-rich crust. Consequently, the magma at Yellowstone is rhyolitic. It is high in silica, making it viscous, sticky, and rich in trapped gases. When this type of magma erupts, it does not flow, it explodes. The magma's chemistry forces the system toward violent, explosive eruptions instead of gentle fountains. And yet, the engine in both cases is identical, a column of hot rock rising from the depths. The scale of these geological engines is almost difficult to comprehend. Some seismic studies suggest that the Hawaiian plume may originate all the way down at the core mantle boundary, a depth of nearly 2,900 kilometers. This is the approximate boundary where the solid rock of the mantle meets the liquid iron of the outer core. If this is accurate, it means the rock that fountains out of Kīlauea today began its upward journey from a region of unimaginable pressure and temperature. While the depth of the Yellowstone plume's origin is more debated, recent studies have traced it far deeper than previously thought, with strong evidence that it too originates well below the upper mantle. These plumes are not only deep, they are also incredibly ancient. The Hawaiian hotspot has been active for at least 80 million years. We know this because the Pacific Plate has been slowly drifting over this stationary heat source for that entire time. As the plate moves, the volcanoes created by the plume are carried away from their source, and a new volcano begins to form in their place. The result is a magnificent chain of seamounts and islands stretching for thousands of miles across the Pacific, marking the path the plate has traveled. This feature is known as the Hawaiian Emperor Seamount Chain, and we will return to its significance. The Yellowstone hotspot, as it turns out, has a very similar and equally impressive track record. As the immense North American plate drifts westward, it passes over the stationary Yellowstone plume, leaving a distinct scar across the landscape. This process has created a chain of ancient calderas that stretch through modern-day Idaho and Oregon. The vast volcanic expanse, known as the Snake River Plain, is, in essence, the geological track marking the continent's journey across this deep-seated heat source. This history, however, raises a fundamental question that is not often explored. Why do two volcanic systems, both powered by a similar type of geological engine, exhibit such radically different behaviors on the surface? The source of heat from below is the same, yet the expression above is wildly divergent. The answer lies in the composition of the rock overlying the plume, as the crust itself shapes the nature of the eruption. But this answer also reveals a profound truth about how much remains hidden from our view. If the surface activity is so dependent on local geology, then the relationship between the deep engine and the resulting event is not direct. It is filtered, mediated, and complex. And it is precisely within this complexity that the current Yellowstone anomaly appears to be hiding, because the deep plume at Yellowstone is not behaving unusually. The surface is. Whatever has changed, it seems, has changed somewhere in between, somewhere within that filter. We will return to this puzzle. But to solve it, we must first understand the system that is behaving as expected, so we can compare it to the one that is not. To truly grasp the events of May 2026, it is essential to frame our perspective correctly. This is not a narrative about some strange coincidence, nor is it a story of a hidden connection. The two volcanic events that occurred in the first week of that month were not synchronized by some unseen mechanism. They were the actions of two independent systems, each following its own geological path at roughly the same moment in human history. That much is clear. Instead, this is a story about contrast. When you place these two distinct events side by side, you gain something far more valuable than either one could offer in isolation. You create a comparison, and that comparison illuminates a reality that neither event could reveal on its own. It is a powerful reminder that in science, context is often as important as the event itself. On May 5th, Kilauea provided the baseline. It was the system operating just as our models understand it. A mantle plume melts the oceanic crust, leading to episodic fountaining, a cyclical release of pressure, and a predictable cadence. We have been studying Kīlauea for more than a century, wiring the volcano with an extensive network of seismometers, GPS stations, gas sensors, satellite radar, and tilt meters. Through this, we can watch as the magma chambers fill, observe the pressure as it builds, and even monitor the conduits as they open and close. So, when Kilauea fountains for 9 hours and expels 6 million cubic yards of basalt, it is not a shock. It is the system confirming that it is still functioning exactly as anticipated. In this sense, the Hawaiian volcanic engine is one of the most well-behaved and understood on Earth. We can almost set our watches by its rhythm. Yellowstone, by contrast, is doing something that our textbooks did not foresee. Specifically, a thermal feature known as Black Diamond Pool, which had sat quietly bubbling for 152 years, suddenly began to detonate. The first of these major explosions occurred in 2024. Then, in late April of 2026, it erupted twice in less than a single day, with the second explosion being even larger than the first. This amounted to 3 significant hydrothermal events in under 2 years, all from a single feature that had shown no dramatic activity since before the United States was illuminated by electric lighting. This raises a question that should send a chill down the spine. What changed? This is where the true mystery begins to unfold, because the honest answer is that no one is entirely sure. The deep signals, which scientists rely on to monitor the volcano's health, are all quiet. The vast seismic networks beneath the park show no unusual stirring in the massive magma chamber. The ground around Yellowstone Lake, a key indicator that scientists watch for signs of pressurization, has not deformed in any alarming way. Furthermore, gas emissions from the wider geothermal system remain within their normal, expected ranges. The deep magma, it seems, is not the source of the disturbance. Therefore, whatever is driving this escalation at Black Diamond Pool is not originating from the main engine room. It must be coming from somewhere shallower, closer to the surface somewhere in the intricate plumbing of the volcano. And it is here, in this shallower realm, that the unknowns begin to multiply. The shallow plumbing of a hydrothermal system, that intricate network of cracks, fissures, and reservoirs that transports superheated water through the rock, is incredibly difficult to map. We have the tools to see the surface and to model the deep magma chamber, but the middle layer, where the water actually moves, pools, and sometimes violently breaks through, is almost entirely invisible to our instruments. We are left to infer its behavior from what emerges at the top. Consequently, when something begins to emerge in unexpected ways, we have very few tools to understand precisely why. So, here is the stark contrast that defines this story. We have two American mantle plumes. One is producing surface behavior that our models predict with remarkable accuracy. The other is generating activity that our models did not predict at all. The critical difference between them does not appear to be what is happening at depth, but rather what is occurring in the parts of the system that we cannot easily observe. To make any sense of the anomaly at Yellowstone, we must first develop a detailed understanding of the baseline at Hawaii. We must walk through what an ongoing, healthy, and well-behaved mantle plume eruption actually looks like. Only then can we truly appreciate how strange the behavior at Yellowstone has become. So, let us journey to Hawaii. Let us go inside what was called Episode 46 and watch a system that is working exactly the way it is supposed to. This will give us the foundation we need to return later and understand why the other system is not. To comprehend what took place at Kilauea on the 5th of May 2026, one must first recognize that this was not a sudden, isolated eruption. It was merely the latest beat in a steady rhythm that had been playing out since December of 2024. It was in late 2024, following a period of relative calm, that Kilauea reawakened at its summit. Specifically, the Halemaumau crater, the central pit at the volcano's peak, began to generate what geologists started referring to as fountaining episodes. These are not continuous, sustained eruptions. Instead, they are discrete, punctuated bursts of volcanic activity. Each episode lasts for a period ranging from a few hours to a few days and is separated by intervals of quiet. During these pauses, the system recharges. In this cyclical process, the volcano fountains, stops, refills, and then fountains again. By the time episode 46 illuminated the night sky over Hawaii's Big Island in early May, the volcano had already produced 45 previous episodes over a span of about 17 months. This works out to an average of one episode every 11 or 12 days, although in practice the spacing was variable. Some episodes occurred only a few days apart, while other pauses stretched for 3 or 4 weeks. Although the volcano's cadence is not perfectly uniform, it is consistent enough for volcanologists to anticipate each event within a fairly tight window of time. The 46th episode in this series was, in many respects, a classic example of this behavior. Its lava fountains soared to a height of 650 feet. While that figure is undeniably immense, It was actually on the lower end of the spectrum for this particular eruption, where earlier episodes had generated fountains reaching as high as 1,400 feet. So, what would be a monumental event for most volcanoes was, in this context, a more moderate display. The resulting plume ascended to 20,000 feet, high enough to touch the lower stratosphere but not to influence global weather. Over a 9-hour period, the eruption released about 6 million cubic yards of material. Again, this is a substantial volume, but it aligns with the system's established output. What is truly remarkable here is the sheer predictability of it all. This is the volcano's baseline rhythm, a cycle of filling, pressurizing, releasing, and refilling. The details may vary, but the fundamental pattern remains constant. This kind of recurring behavior reveals something fundamental about the mechanics of mantle plume volcanism. When the internal plumbing is mature and the system is operating in a stable mode, the magma chamber beneath the summit serves as a crucial buffer. It takes in a steady supply of new magma from deep within the earth and releases it in discrete batches, only when the internal pressure is great enough to fracture the rock containing it. This is the reason the eruption is episodic, rather than a continuous flow. The system simply requires time to recharge between each release, almost as if it were breathing, and the regularity of that breath tells us something vital about its current state. A system that breathes in such a regular rhythm is, for the moment, a contained one. Despite the breathtaking spectacle of 6-story lava fountains and ash plumes climbing nearly 4 miles into the sky, all of this activity has been confined to the summit caldera. There have been no eruptions along the volcano's flanks, no lava flows threatening populated areas, and no activity in the rift zones. In a way, the volcano is putting on a magnificent show while keeping the real danger in check. This containment is not an accident. It is a clue. It offers insight into the system's present configuration and hints at what might happen next. While this pattern of episodic fountaining defines the current behavior, mantle plume volcanoes are not known for staying in one mode indefinitely. The rhythm we are witnessing now is merely a single chapter in a much longer and more complex story. When the next chapter begins, it may not resemble this one at all. So, what is the underlying engine driving these clean, repeatable cycles? To find the answer, we must examine the one part of the volcano that is rarely discussed, its pressure cycle. Imagine a kettle filled with water, sitting on a lit stove. As heat is steadily added, the water grows hotter and the pressure inside the kettle builds. Eventually, that pressure becomes so great that it forces steam out through the spout, creating a whistle. Once enough steam escapes, the pressure drops, the whistling stops, and the entire process prepares to begin again. In a very simplified sense, this is what is happening at the summit of Kilauea. The molten rock is the water. The mantle plume is the stove, and the container is a complex network of magma chambers and conduits woven into the volcano's structure. The principle, however, remains the same. Energy enters, pressure accumulates, the system finds a release, and the cycle repeats. In slow motion, the process begins as magma ascends from the upper mantle into deep storage zones beneath the volcano. From there, it migrates into shallower chambers closer to the surface. As this chamber fills, the pressure on its walls, which are made of cooler, solid rock, steadily increases. These walls can only withstand so much force before they begin to fail. When the internal pressure finally overcomes the strength of the surrounding rock, fractures propagate upwards, creating a pathway to the surface. This is the moment of eruption. Once the eruption starts, the pressure begins to fall almost immediately. The magma that was held in waiting now has an escape route, and it rushes upward, fountaining from the vent and pooling as fresh lava on the crater floor. As the pressure continues to drop, the force driving the eruption weakens. Eventually, it is no longer strong enough to push magma to the surface. The fountain subsides, the vents begin to seal themselves, and a period of quiet returns. Then, the entire cycle of accumulation and release starts anew. What is particularly interesting, and what matters for understanding the larger story, is that this cycle has become progressively more refined over time. The episodes during the initial months of the eruption were far more variable. Some were short and intense, others were long and drawn out, and some produced fountains of unusual height or strange, irregular shapes. But as the eruption has matured, the cycles have settled into a more regular and predictable pattern. The system appears to be optimizing itself. This phenomenon is not unusual in nature. Many natural systems evolve to become more efficient at transferring energy. A river, for example, first carves a winding, inefficient path across a landscape. But over millennia, erosion smooths the channel, creating the most direct route for water to flow. A similar process of self-organization occurs in a volcano's plumbing. Each eruption subtly alters the network of conduits. Pathways that allow for an efficient release of pressure are reinforced, while those that are less effective become sealed off. Over many cycles, the system converges on the configuration that releases pressure in the most streamlined way possible. This observation, however, raises a critical question that brings us back to our central theme. If the system at Kilauea is currently optimizing itself for clean, regular pressure release, what does that imply for its future? Does an efficient pressure release mechanism mean the eruptions will remain small and predictable indefinitely? Or could this period of stability be the prelude to a more significant change? Does this growing regularity imply that when a disruption finally occurs, its effects will be far more dramatic than anything we are witnessing today? A definitive answer to that question remains elusive. However, a comparison with Yellowstone provides a telling contrast. The hydrothermal system at Yellowstone's Black Diamond Pool appears to be evolving in the opposite direction of Kilauea. Rather than settling into a smoother, more predictable pattern, it is growing increasingly erratic. Instead of converging toward a clean cycle, it is diverging into something new and unknown. This suggests that whatever self-optimizing process is making the Hawaiian volcano more rhythmic is either absent in Wyoming or is operating on an entirely different timescale. So, we can see that the system at Kilauea is currently in a phase of relative stability, defined by a cyclic mode of operation. Pressure accumulates, releases, and then builds once more, with a regular cadence and contained output. For now, the volcano seems to be breathing on its own schedule. Yet, there is more to a volcanic system than pressure alone. Its internal geometry is equally crucial. The shape of the plumbing matters just as much as the force within it, and the geometry of Kilauea's vents has been revealing its own fascinating story. Part 8. The geometry of the vents. If one were to peer down into the Halemaumau crater from an overlook, the view is essentially of a basin nested within another basin. The vast outer caldera forms a large depression several miles across. Within that depression lies the crater itself, a smaller, deeper pit, and scattered across the floor of this inner pit are the vents, the physical openings through which molten rock reaches the air. Throughout most of the current eruption, two principal vents have been responsible for the majority of the activity, a north vent and a south vent. Positioned relatively near one another on the crater floor, they have historically taken turns as the primary source of lava. At times, the south vent was more vigorous. At other times, the north vent dominated. On occasion, they have erupted in unison, creating twin fountains of lava that merged into a single, broader curtain of fire. This delicate balance, however, was about to change. Episode 46 of the eruption was unusual for one particular reason. The north vent performed almost all of the work. The south vent, which had been a significant contributor in previous episodes, remained largely quiet for the duration of the 9-hour event. The spectacular 650 8-foot tower of lava that defined this episode emerged almost exclusively from the north vent, with the south vent contributing virtually nothing to the display. At first glance, this might seem like a minor technical detail. Why does it matter if one vent was more active this time? It matters profoundly because it offers clues about the subterranean pathways that magma is carving on its journey to the surface. And those pathways are clearly evolving. When a volcano establishes a new route for its magma supply, the initial pathways are often irregular and complex. Magma is an opportunistic force, exploiting whatever existing cracks and fractures it can find. Consequently, the early phases of an eruption often involve multiple vents activating in a somewhat random fashion, depending on which channels happen to open at any given moment. But as an eruption persists, a process of consolidation begins. Certain pathways become preferred routes. The continuous flow of extremely hot magma through a particular conduit gradually widens it, smooths its walls, and makes it more thermally efficient. In time, the most efficient pathway becomes the dominant one, causing other, less efficient routes to begin to seal off. This process is strikingly similar to the formation of a river system, though on a much faster timescale. When water first flows over a flat landscape, it spreads out into countless small channels. Over time, the channels that carry the most water erode their beds more deeply, capturing flow from the smaller rivulets until a single main river and its tributaries emerge. The vent geometry at Kilauea appears to be undergoing a similar consolidation. The evidence suggests that the north vent is steadily becoming the primary, dominant pathway for magma. The south vent, which was so active during many of the earlier episodes, is now being progressively bypassed. If this trend holds, we might expect future eruptive episodes to be almost entirely dominated by the north vent, with the south vent perhaps sealing off completely. What does this tell us about our central story of the volcano's behavior? It reveals that even after 17 months of eruption, the system is still in the process of organizing itself. It has not yet achieved a final, stable equilibrium. The system is converging, but the convergence is not yet complete. This ongoing reorganization is precisely what makes the Hawaiian baseline so valuable. We are witnessing, in real time, a mantle plume volcano sorting itself out, like an engine, smoothing its own cylinders. But there is a crucial flip side to this process. A system that locks into a single dominant pathway also becomes more vulnerable to specific kinds of disruption. If the north vent is shouldering all the work and something were to obstruct it, the immense pressure building beneath would not simply vanish. Instead, it would begin searching for another way out. And in a volcano, when trapped pressure starts looking for an escape route, the consequences can become dangerously unpredictable. So, while the surface activity paints a picture of increasing stability and order, the deeper reality is that of a system placing more and more of its eggs in one basket. This trade-off between stability and fragility is a theme we will return to. Because if the current configuration is indeed becoming locked in, then any future deviation from this pattern will likely not be subtle. It will be dramatic. And that brings us to the part of the story that looms over every observation. The thing that should be happening, but is not. Part 9. The missing escalation. Anyone who has followed news from Hawaii's volcanoes for any length of time will remember the events of 2018. That summer, Kīlauea did something it had not done on that scale in living memory. It erupted not from its summit, but from a location called the Lower East Rift Zone, dozens of miles away from Halemaumau. Lava poured from fissures that opened in the ground within residential neighborhoods. Hundreds of homes were destroyed as entire subdivisions, like Leilani estates, were buried beneath fresh lava flows. Roads were severed, and coastal landscapes were permanently reshaped. The 2018 Lower East Rift Zone eruption was a stark reminder that Kilauea is not merely a summit volcano. it is a volcano with multiple personalities. It can erupt at its summit, where the spectacle is largely contained within the caldera, or it can erupt along its flanks. This happens through a network of long fractures known as rift zones, which extend for many miles in either direction from the summit area. When an eruption occurs along one of these rift zones, the consequences for human populations can be enormous. And so, this is the question that should hang over our entire conversation about Kilauea's current, seemingly stable behavior. With episode 46 and all the preceding events unfolding at the summit, a natural question arises. Why is all the activity concentrated here? The volcano has clearly demonstrated its ability to erupt along its rift zones, so why isn't magma finding an escape route along the flanks? The most compelling answer seems to lie in the interplay between pressure and geometry. At this moment, the summit provides the path of least resistance. Magma ascending from the deep plumbing system finds it easier to travel through the summit conduits than to force its way into the rift zones. Consequently, as long as these summit pathways remain open and efficient, they act as a release valve, keeping the rift zones dormant. But this apparent stability is deceptive, as the underlying magma supply from the mantle plume has not diminished. Hot rock continues to feed the system at a rate consistent with previous decades, and all of that material must go somewhere. For now, it escapes through the episodic fountains at the summit. This leads to an unsettling thought. What happens if that summit pathway becomes blocked? What if the primary northern vent, which has been so active, seals itself shut? Or what if the system simply reaches the maximum rate at which it can sustainably erupt from the summit? In any of these scenarios, the pressure would need a new outlet, making the rift zones the most likely alternative. Any pressure unable to vent at the summit would seek another exit, and history shows that exit has often been through the east or southwest rift zones, both of which cut through populated and economically vital areas of Hawaii Island. This situation has given rise to a hypothesis quietly discussed among volcanologists. The theory suggests that the ongoing summit eruption is effectively acting as a buffer for the entire system, absorbing pressure that might otherwise be destined for the rifts. According to this view, the longer the summit continues its current eruptive cycle, the longer the rift zones will remain quiet. Yet, this buffering capacity is not infinite. At some point, the system is expected to shift, and no one can predict precisely when that will happen or how much advance warning we might receive. This brings us back to a central theme of our exploration. We have described Kilauea as a baseline, a well-behaved system, performing exactly as anticipated. While this is true, a layer of profound unease lies just beneath that predictable behavior. The more efficient and consolidated the current cycle becomes, the more difficult it is to forecast what will happen when that cycle inevitably breaks. And in the world of volcanoes, all cycles eventually come to an end. It is a fundamental aspect of their nature. The monitoring networks observing Kilauea are among the most sophisticated on Earth. A vast array of seismometers, GPS stations, tilt meters, gas sensors, satellite radar systems, infrared cameras, and webcams are trained on every critical part of the volcano. It is highly probable that when the system does begin to change its mode of operation, we will detect some warning signs. The crucial question, however, is not whether we will see these signs, but whether we will see them in time and correctly interpret their meaning. So even here, in this baseline system, uncertainty persists. It is simply a different kind of uncertainty from what we encounter at a place like Yellowstone. For Kilauea, the uncertainty is about times when the current mode will end. For Yellowstone, it is about times the current mode is happening at all. In their own ways, both systems remind us that the boundaries of our knowledge are much closer than we might prefer to believe. To truly grasp this, we must step back and view Hawaii not on a scale of months or years, but on the vast timescale of millions of years. On that scale, Kilauea is not the final chapter. It is merely the latest word in a story that has been writing itself for an immense period of time. If you were to examine a bathymetric map of the Pacific Ocean, one that reveals the topography of the seafloor, you would discover a truly extraordinary feature. Stretching from the Hawaiian Islands all the way to the Aleutian Trench off the coast of Russia is a long, almost impossibly continuous chain of underwater mountains. This chain is not a perfectly straight line. It bends sharply about halfway along its length, but it remains an unbroken, single volcanic feature that spans thousands of miles. This remarkable structure is known as the Hawaiian Emperor Seamount Chain. It is the physical track of the Hawaiian mantle plume etched across the floor of the Pacific Ocean over the last 80 million years, a silent testament to deep geological forces. The mechanism behind its creation is a fascinating dance between a stationary plume and a moving plate. The Hawaiian plume, that deep column of hot rock we have been discussing, has remained in roughly the same location beneath the Pacific Ocean for some 80 million years. While it may have shifted slightly over geologic time, it has largely stayed in the same cosmic neighborhood. Meanwhile, the Pacific Plate, the section of Earth's crust upon which the seafloor is built, has been steadily moving for tens of millions of years. This plate has been sliding to the northwest at an average speed of about 4 inches per year. Imagine the process. The fixed plume acts like a blowtorch, punching a volcano up through the crust. The moving plate then carries that newly formed volcano away from the plume's heat source. As the plate continues its journey, a new volcano begins to form over the hotspot. This cycle has repeated itself for 80 million years, creating a chain of volcanoes that grow progressively older the farther they are from the active plume. The youngest volcano is the one currently situated over it, essentially, the big island of Hawaii, home to Kilauea. The next youngest are the other Hawaiian islands like Maui and Oahu, each older as one moves northwest. Beyond Kauai, the chain submerges, continuing as a series of seamounts that have been eroded below the ocean's surface, all the way to the Aleutian Trench, where the oldest are finally being recycled back into the mantle. What makes this geological story even more compelling is a distinct kink in the chain. About halfway along its length, the chain makes a sharp bend. The younger, Hawaiian portion runs in a roughly east to west direction, while the older half, the Emperor Seamounts, is aligned north to south. This bend is dated to approximately 47 million years ago. It represents a significant moment in geological history, recording either a change in the direction of the Pacific Plate's movement, a shift in the position of the plume itself, or some combination of the two. While the exact cause remains a subject of scientific debate, the bend itself is undeniably there, frozen into the seafloor's topography like a permanent record of a time when the rules suddenly changed. And this is where the story takes another surprising turn. A new Hawaiian island is already taking shape, though it has yet to breach the ocean's surface. Roughly 20 miles southeast of the Big Island, a young submarine volcano named Kaimaiwa, formerly known as Lohe, rests on the seafloor. Currently submerged about 3,000 feet deep in the Pacific, it is actively growing. This nascent island is fed by the very same mantle plume that supplies magma to Kilauea. Over vast stretches of geologic time, Kaimaiwa is expected to ascend, eventually emerging from the waves to join the Hawaiian archipelago. In a parallel process, the Big Island is drifting northwest and will, over millennia, succumb to erosion and sink beneath the sea, following the fate of its predecessors. This cycle of creation and decay reminds us that the events we witness are but fleeting moments. The activity at Kilauea is neither a beginning nor an end, but simply a point within an immense 80 million year narrative. The fountain observed in May 2026 was in geological terms, like a single exhalation from a life form of immense longevity. This perspective is vital as we turn our gaze to another great system, Yellowstone. Like Hawaii, the Yellowstone hotspot possesses a long and storied history, etched across the North American continent. Its journey is chronicled in the formation of the Snake River Plain and a series of ancient calderas that trace the plate's movement over the mantle plume. Yet, unlike its Hawaiian counterpart, Yellowstone is currently exhibiting surface activity that seems to defy the predictions of its deep geological timeline. This strange discrepancy is the central puzzle we seek to understand. It is time to shift our focus from a system behaving as expected to one that is acting in a profoundly unusual way. We journey now from the predictable volcanic fountain to a series of baffling explosions, from Hawaii to Wyoming, to investigate a single thermal pool that has begun to detonate for reasons that remain elusive. The unsettling events at Black Diamond Pool began on the 28th of April, 2026. The initial explosion was heralded by a low rumble and a sudden crack, followed by a powerful eruption of water, mud, and debris into the sky. The force was significant enough to launch boulders from the pool, while the nearby boardwalk was blanketed in a layer of fresh mud and rock. For several minutes after the main blast, steam continued to pour from the site. At first, the incident seemed straightforward. Park geologists who arrived to survey the scene classified it as a hydrothermal explosion. They noted the visible changes, the pool's altered shape, collapsed ground nearby, and shifts in the water's level and chemical composition. Everything pointed to a standard, albeit powerful, geological release. According to the established model for such events, this explosion should have served as a release valve. The immense pressure that had accumulated within the subterranean system was now vented. The underground conduits should have been cleared, allowing trapped superheated water to escape. Following this release, the entire system was expected to stabilize into a new, lower pressure equilibrium. This calmer state would then persist for a considerable time before the cycle of pressure buildup might slowly begin again. This is the textbook progression, the predictable outcome of a hydrothermal blast. But what happened next defied all expectations. On April 29th, less than a full day later, Black Diamond Pool erupted once more. This second explosion was not only unexpected, but it was also more powerful than the first. This is the detail that is so profoundly strange. If the initial blast had indeed released the system's pressure, a second explosion should have been impossible, or at the very least, far weaker, fueled only by any remaining pressure. Its greater magnitude implies that during the brief 2-4 hour interval, the pressure within the local plumbing did not just recover, it intensified. This raises a critical question that currently perplexes geologists. How can a hydrothermal system that has just vented its energy manage to repressurize so rapidly and violently in under a day? While no single explanation is universally accepted, several hypotheses attempt to account for this anomaly. One possibility is that the first explosion was incomplete, failing to fully unblock the conduits and release the accumulated pressure as initially thought. Another theory suggests the initial blast may have altered the underground plumbing, fracturing rock in a way that connected the surface vent to a previously isolated, higher pressure reservoir deeper below. A third, more concerning scenario posits that the second blast was not caused by pre-existing pressure at all, but by a new and rapid injection of energy from deeper within Yellowstone's volcanic system. Each of these possibilities is unsettling in its own way, as they all suggest that our standard models of hydrothermal activity are insufficient to explain the behavior of Black Diamond Pool. This mystery brings us directly back to our central theme. At Kilauea, we observe a system that operates with remarkable predictability. Pressure accumulates, a fountain erupts, the pressure subsides, and the cycle repeats with a certain rhythm. This consistent pattern serves as a near-perfect example of a healthy volcano fed by a mantle plume. At Yellowstone's Black Diamond Pool, however, the pressure cycle is behaving erratically. A release is followed by an unexpectedly rapid and more potent buildup, culminating in a more violent eruption. Here we have two systems with similar deep geological origins, yet they display completely different patterns of surface behavior. It is this stark contrast between the predictable and the chaotic that forms the heart of our investigation. What, then, is happening deep within the subterranean network beneath Black Diamond Pool? What mechanism could enable a hydrothermal system to recharge with such speed and force after a major release? To begin to formulate an answer, we must venture away from the surface and peer into the complex world of the underground cracks and fissures. The most prominent hypothesis favored by hydrothermal geologists, the one that offers the most plausible explanation for the double explosion, centers on a gradual process with sudden, dramatic effects. The key lies in the chemistry of silica. The water circulating in these hydrothermal systems is rich in dissolved silica, which it leaches from the surrounding rock as it flows. This silica remains dissolved as long as the water remains extremely hot and under high pressure. However, if that water begins to cool, or if the pressure lessens, the silica can no longer stay in its dissolved state. It begins to precipitate, depositing solid material onto the inner surfaces of the underground cracks and channels. It is a slow, insidious buildup, with these silica deposits accumulating year after year, decade after decade, gradually constricting the flow. Over long periods, the underground channels that feed a geyser can begin to narrow. As mineral-rich water flows through them, it deposits layers of silica, gradually restricting the plumbing and making the system more enclosed. This process can unfold for decades or even centuries, with no obvious signs at the surface, save for a bubbling pool or unusually hot water. Beneath the feet of unsuspecting visitors, a seal is slowly forming. Yet, the pressure from the heated water deep below does not simply vanish. It continues to build, trapped behind an ever-thickening mineral plug. Then, a critical threshold is crossed, and the seal fractures. Suddenly, the water that has been held under immense pressure is given an escape route. As it surges upward, the confining pressure drops, causing the water to flash into steam. In this transition from liquid to vapor, it expands with incredible force, growing to roughly 1,500 times its initial volume. This sudden, violent expansion is the heart of a hydrothermal explosion. If this model applies to Black Diamond Pool, the first blast on April 28th would represent the moment that delicate silica seal finally broke. This explanation, however, introduces a compelling question. If the first explosion was the system releasing its pressure, why did a second, larger one follow so quickly? The leading explanation, known as the plumbing hypothesis, suggests that after being sealed for 152 years, the volume of trapped, superheated water was immense. The initial explosion may have only cleared a portion of the blockage, uncorking the uppermost section of the plumbing. This left a deeper, larger reservoir of pressurized water still below, now with a freshly opened path to the surface. Less than 24 hours later, this deeper reservoir surged upward. Because it traveled a greater distance and contained more stored energy, the resulting explosion was even more powerful than the first. This idea of a multi-stage release from a long-sealed system remains the most straightforward interpretation of the events we have observed. Of course, science demands we consider alternatives. Another possibility is that a new surge of heat from deep within the Earth is responsible for the heightened activity at Black Diamond Pool. In this scenario, the change would not be a passive release of stored pressure, but an active increase in the energy being fed into the system. This could be caused by a new pathway opening from the magma chamber, or perhaps a small intrusion of fresh magma far below. It is a dramatic thought. but one that currently lacks supporting evidence. The problem with this hypothesis is that Yellowstone's deep monitoring network is not detecting the telltale signs of such an event. Instruments that measure ground deformation show no unusual swelling. Seismic sensors have not picked up any anomalous earthquake patterns, and the general gas chemistry across the park remains unchanged. While a fresh input of heat cannot be entirely ruled out, the available data does not favor this explanation. This is where a crucial distinction comes into focus. When observing volcanoes in places like Hawaii, we can often see the inner workings of the magmatic engine. Data from ground deformation, gas emissions, and seismicity paint a clear picture of magma moving through a relatively well-understood plumbing system. At Yellowstone, however, the deep signals are quiet. The engine room is not sending any unusual messages. This strongly suggests that whatever is driving the escalation at Black Diamond Pool is happening at a shallower depth, above the primary magma chamber, within a tangled network of cracks and conduits that are incredibly difficult to image directly. The mystery, it seems, is not in the deep basement of the volcano, but on one of the floors just below the surface. Our greatest blind spot is not miles down, but tantalizingly close. If the plumbing hypothesis holds true, then what we are witnessing may be the beginning of a longer sequence of events. The system could be in the process of reorganizing its shallow architecture after a century and a half of slow, silent sealing. This would mean the recent explosions are not isolated incidents, but rather the first expressions of a new, more active pattern. The timeline of events at Black Diamond Pool lends weight to this unsettling idea. The rate of change itself tells a story that demands our attention. Before 2024, the pool had not undergone a major hydrothermal explosion for 152 years. It was a stable feature, bubbling and steaming but not exploding, considered dormant in its explosive capacity. For generations, it was just one of many beautiful hot springs in a park filled with them. That long period of stability ended in 2024. A significant hydrothermal explosion rocked Black Diamond Pool, throwing boulders and damaging nearby boardwalks, prompting park officials to close the area. At the time, it was viewed as a notable but singular event, the logical conclusion of pressure building up over a long period. The prevailing interpretation was that the system had released its stress and would now settle into a new, lower pressure state of equilibrium. This was the standard model. Then, less than 2 years later, in late April of 2026, the pool erupted twice in just 24 hours, with the second blast being the more powerful of the two. The tally suddenly shifted from 0 major events in 152 years to 3 significant explosions in less than 2. This is not a gradual escalation. It is a step change, indicating the system has decisively transitioned out of its prior, stable regime and into something new and far less predictable. To place this in context, hydrothermal explosions themselves are not unheard of in Yellowstone. With thousands of thermal features, small steam explosions occur somewhere in the park every year. Larger, more significant explosions are less common, happening on average just once or twice per decade across the entire park. What makes the situation at Black Diamond Pool so unusual is the concentration of multiple, powerful events at a single feature within such a compressed time frame. It strongly suggests that something specific to the local plumbing of this one pool has fundamentally changed. Scientists describe this using the language of equilibrium. A stable system can exist in one state for a very long time, only to transition, sometimes suddenly and dramatically, to a new state of balance. Black Diamond Pool appears to be caught in the midst of such a transition. The old equilibrium, the one that defined it from the 1870s until 2024, is now a thing of the past. A new equilibrium has not yet taken hold. The system is currently in a liminal state, caught between one phase and the next, and during such transitions, its behavior becomes unpredictable. This kindis reminiscent of processes that geologists have documented in other geyser systems around the world. It is not unheard of for a geyser that has lain dormant for decades to suddenly spring back to life, or for a geyser with a predictable eruption schedule to fall silent. The causes for these shifts are typically local in nature: a change in the subterranean plumbing, a fluctuation in the water table, or a minor nearby earthquake that alters the underground network of cracks. The vast, deep, magmatic system is rarely the immediate driver. Instead, the cause is usually something shallower and more localized, something our instruments cannot directly observe. This is where the comparison to Hawaii becomes so illuminating. In Hawaii, we are witnessing a system that is gradually stabilizing and becoming more regular over time. At Yellowstone's Black Diamond Pool, however, we see the opposite, a system growing less regular, more chaotic. Both systems are in a state of evolution, but they are moving in contrary directions. This escalation at Black Diamond Pool serves as powerful evidence of hidden variables within plume systems, factors that our current models have not fully captured. It suggests that the deep engine, the broad hotspot itself, can remain stable while a single feature on the surface undergoes a dramatic and violent reorganization. That reorganization tells us that forces are at work within the geological plumbing that we are only just beginning to understand. So, if the surface anomaly at Black Diamond Pool is not being driven by a change in the deep system, what is that system actually doing? The answer, it turns out, holds its own profound surprises. In recent years, seismic tomography studies of the Yellowstone region have yielded a discovery that has genuinely transformed how scientists perceive this hotspot. Tomography is a method that allows us to create a kind of CT scan of the Earth's interior by using waves from earthquakes. As these seismic waves travel through the planet, their speed changes depending on the temperature and composition of the rock they pass through. By recording these waves at numerous stations and analyzing the variations in their travel times, scientists can construct a three-dimensional model of the subsurface. What this recent tomography has revealed is that the deep heat source feeding Yellowstone, the actual mantle plume, is not located directly beneath Yellowstone National Park. In a stunning twist, it is offset. The root of the plume sits hundreds of miles away from the caldera, deeper within the mantle. From there, the heat travels laterally through the crust before it rises to the surface, creating the volcanism we see. In essence, the chimney is not positioned directly over the fire. There is a significant bend in the plumbing. This finding is critical because it means the area where dangerous activity could theoretically occur is not confined to the familiar boundaries of Yellowstone National Park. The true deep system extends far beyond the park, reaching into Idaho and possibly even parts of Nevada. The borders we see on a map, which were drawn in the 1870s to define the park, are purely administrative and have no bearing on the geometry of the deep heat source. The plume, of course, pays no mind to such human-drawn lines. This realization connects directly back to our central theme, reinforcing just how poorly we have mapped these deep systems. Scientists have known about and studied the Yellowstone hotspot for decades, writing countless textbooks on the subject. Yet, it is only recently that we have discovered the deep source is fundamentally offset from its surface expression. This is not a minor adjustment to our models. It is a complete restructuring of our understanding of where the system truly resides. It begs a humbling question. If we were wrong about the basic geometry for so long, what else might we be getting wrong right now? Building on this, the practical implication of the offset plume is that the risk envelope around Yellowstone is considerably larger than the park's boundaries would suggest. Geothermal anomalies have been identified in parts of Idaho that may be connected to this broader system, and there are areas of unusual heat flow that align with the inferred path of this lateral heat transport. While this does not imply an eruption is imminent in Idaho, the risk of any near-term event remains very low. it does mean the area that should be monitored as part of the same geological system is much larger than the park itself. There is also some speculation, though the evidence is still thin, that certain geothermal signatures in the region could indicate connections to other heat sources farther west. Whether these are part of the same plume or independent features is not yet clear. The data is insufficient to support a firm conclusion, but the very existence of this speculation has prompted some researchers to argue for a greatly expanded scope when assessing mantle plume risk in the United States. This brings us back once more to the recurring lesson of this entire story, the mismatch between what we can see and what is actually shaping the danger. The boardwalk where Black Diamond Pool erupted can appear as a tranquil hot spring on any given day, while the deep source feeding the entire Yellowstone system sits hundreds of miles away. The surface, it seems, is an imperfect and often misleading translator of the immense forces at work below. But while science grapples with these implications, the internet has already formed its own conclusions. If you were on social media during the first week of May 2026, you undoubtedly encountered the narrative, and it was everywhere. The Earth, it was claimed, is waking up. The tectonic plates are shifting. The hotspots are activating. A torrent of posts declared that Yellowstone was rumbling, Hawaii was fountaining, the Aleutian Islands were shaking, the Philippines were trembling, and the Kermadec Trench was groaning. The message was clear. Something big is coming. The planet is sending us a sign. The evidence was presented in video clips stitched together with dramatic music, on maps dotted with ominous red circles, and through voiceovers that were urgent, breathless, and absolutely certain of an impending global event. Within just a few days, video compilations of dramatic global events were viewed by tens of millions of people. In the comments, a single sentiment echoed again and again. We knew this was coming. It's finally happening. Our time is running out. It is tempting to dismiss these claims, but it is far more important to take the reaction itself seriously. The reason for this is not because the central assertion is accurate. In fact, it quickly crumbles under careful examination. Instead, the impulse driving this belief is profoundly worth our consideration. There is a deep, underlying reason why millions of otherwise thoughtful and skeptical individuals could watch these clips and feel, with visceral certainty, that they were witnessing a genuine pattern. This raises a crucial question. What is this powerful feeling, and where does it come from? That gut feeling is not a sign of foolishness or gullibility. On the contrary, it stems from one of the most ancient and effective adaptations in the history of life on Earth. Our very minds are constructed to be pattern-seeking instruments, designed to identify connections between events even where none may actually exist. This is not a defect in our programming. It is a vital survival mechanism, refined over millions of years in the forests and savannas our ancestors called home. The early hominid who learned to associate the rustle of leaves with an approaching predator was far more likely to survive than one who did not. Likewise, the individual who connected the faint smell of smoke on the wind with the danger of a spreading fire lived to pass on their genes. This instinct for pattern recognition is what kept our ancestors alive, and in a very direct sense, it is why you are here to experience this moment. The same mental architecture that allows you to perceive a face in the clouds, hear your name called in a crowded room, or feel the gaze of a stranger is the very machinery that saved your distant relatives from harm. Herein, however, lies the fundamental challenge. That remarkable cognitive machinery was calibrated for a world of immediate, local, and high-stakes information. The rustling in the bushes was a meaningful signal, because the predator was, in fact, just meters away. Our brains evolved to find patterns within a small, physically present landscape. They were never designed for the world we inhabit today. This ancient system was not built to process the relentless stream of 2 4-hour cable news. Nor was it prepared for global content aggregators or the algorithms that power them. It was certainly not equipped for a technology that can gather every dramatic event from every corner of the globe in real time, package it into a minute-long video, and deliver it to you as you begin your day. In our modern era, we are connected to streams of data that our ancestors could never have imagined. Every earthquake exceeding a magnitude of 4, no matter where it occurs on the planet, is logged, mapped, and shared in a matter of minutes. Every volcanic eruption, however minor, is capable of generating media coverage somewhere in the world. Similarly, every unusual weather formation, every major wildfire, every sinkhole, and every display of the aurora borealis is likely to be photographed, posted online, and amplified through networks that span the entire globe. We are no longer just observing our immediate surroundings. We are plugged into a planetary-scale sensory system. Consequently, when we open our devices, we are not witnessing the world our brains evolved to understand. Instead, we are presented with a curated, compressed, and intensely edited highlight reel, showcasing the most notable occurrences from a planet of 8 billion people spread across nearly 200 million square miles of land and sea. In the face of this extraordinary input, our pattern recognition machinery, still operating on its ancient firmware, simply does what it was designed to do. It seeks out connections. It draws lines between the dots, and with unwavering conviction, it tells us that all of this must signify something important. The truth is that the vast majority of these perceived connections are purely coincidental. Our Earth is a noisy, energetic, and perpetually active system. At any given moment, there are approximately 50 volcanoes erupting somewhere on the planet. Every single week, hundreds of earthquakes above magnitude 4 occur. Beyond that, countless smaller events, thermal anomalies, mudslides, landslides, icequakes, and atmospheric disturbances happen daily. Yet they never capture our attention because they lack the dramatic quality needed to be clipped and shared. So, when our screens show us a lava fountain in Hawaii, an explosion in Wyoming, an earthquake in Alaska, and a tremor in the Philippines all in the same week, our brains insist that this must be a coordinated sequence. The reality, however, is that weeks like this are far more common than we think. We only tend to notice these occurrences when a particularly dramatic event serves to crystallize the pattern in our minds. In the week before such a video appears, and in the week that follows, a similar number of geological events were likely taking place. We simply weren't looking for them, because the compilation that would connect them had not yet been created. This phenomenon is well known in the field of statistics, where it is called survivorship bias. In this context, however, it might be more accurately described as attention bias. The data points that capture our focus are not a random sample of all that is happening. They are the points that have been specifically selected for us to see. Once a handful of notable events are selected and presented to us as a cluster, our minds instinctively finish the task. We perceive the grouping, we feel the significance, and we construct a narrative to explain it all. This story can feel so profoundly true and self-evident that to even question it can feel like an act of denial. It can make us feel as though we are the ones burying our heads in the sand, refusing to acknowledge a pattern that seems obvious to everyone else. It is important to understand this feeling, because it is a deeply human one. I have felt that same magnetic pull myself on more occasions than I care to admit. The experience of perceiving a hidden order within chaotic events is among the most powerful sensations the human brain can generate. This feeling activates the same neural circuits associated with spiritual revelation, the euphoria of falling in love, or the satisfaction of solving a difficult puzzle after hours of effort. Our brains offer a deep cognitive reward for connecting the dots. Furthermore, the more profound and far-reaching the perceived connection, the greater the neurological reward. This leads to a critical insight. The patterns that spread most rapidly across social media, the ones that achieve true virality, are not necessarily those that are factually correct. Instead, they are the ones that provide the most potent, cognitive, and emotional payoff when they are believed. This selection filter, based on emotional resonance, is fundamentally different from the one that produces accurate and reliable models of the world. This brings us back to the central thread of our inquiry, and it is a connection worth making explicit. There is a crucial difference between a time's perceived pattern times and a time's real unknown, and confusing these two concepts is precisely how public discourse on such events becomes derailed. The perceived pattern is the narrative of a global awakening, the idea that the Earth is communicating with us, that geological hotspots are acting in concert, that the ring of fire is pulsing with intent, or that the tectonic plates are conspiring. None of these dramatic interpretations are supported by the available evidence. Learning to distinguish between the story our minds want to tell and the facts the data actually show is the essential challenge before us. The human mind is a powerful pattern recognition machine, but sometimes it constructs stories from scattered events, seeing a unified whole where none exists. This is a critical distinction to make, because the real mystery is not some imagined global pattern, but something far more specific and localized: the recent behavior of Black Diamond Pool. Here we have a tangible, well-defined enigma. After 152 years of quiet, this single pool has generated 3 major explosions in less than 2 years, with the second of the latest pair being even larger than the first. Scientists currently lack a confident explanation for this rapid escalation, as the data does not yet favor one potential mechanism over another. This is a genuine gap in our understanding. The difference between a perceived pattern and a real unknown is fundamental. Perceived patterns tend to dissolve under scrutiny, revealing there was nothing substantial to begin with. A real unknown, however, only becomes sharper and more defined the closer you look. Belief can satisfy a perceived pattern, but a real unknown demands evidence. One of the most vital disciplines for clear thinking is to keep these two categories mentally separate. The public conversation often goes astray precisely because this distinction is lost. Conspiracy theories can inflate a perceived pattern into a cosmic event, while official statements may deflate a real unknown into mere routine monitoring. Both reactions miss the heart of the story. There is indeed something unsettling happening in the first week of May 2026, but it is not a global awakening. The true focus should be on a single pool that is not behaving as expected. The signal to heed is not the noise of 100 unrelated incidents, but the clear signal from one specific feature on American soil that is doing something we cannot yet explain. This brings us to a potential, if unconventional, explanation, the solar activity hypothesis. It is the kind of fringe idea that, despite thin evidence, warrants careful examination. Here on Calm Space, we believe in exploring concepts that exist outside the comfortable consensus. Our approach is not to dismiss such ideas, but to investigate them, test their foundations, and see how much weight they can truly bear. Some collapse under pressure almost immediately, while others reveal a kernel of truth. The only way to distinguish between them is to afford them the respect of a serious, careful look. It is in this spirit of open-minded but critical inquiry that we consider the question of whether the sun's activity could influence events deep beneath our feet. To understand this hypothesis, we need some context. We are currently in or near the peak of solar cycle 25. This is the latest of the sun's 11-year cycles of activity, which scientists have been systematically tracking since the 1700s. Our sun is not a static ball of fire. It is a dynamic star that pulses and breathes. Its magnetic field even flips its polarity on a regular schedule. As this cycle unfolds, the activity on the sun's surface waxes and wanes. During the quiet phase, known as solar minimum, the surface is relatively clear, with few sunspots and only weak, infrequent flares. The corona, that ethereal halo of plasma surrounding the sun, becomes calm. Conversely, during the active phase, or solar maximum, the surface erupts. Sunspots multiply, flares grow more frequent and violent, and coronal mass ejections, enormous bubbles of plasma and magnetic fields hurled into space, become more common. Right now, in the spring of 2026, we find ourselves near the zenith of this latest active phase. This has led to increased speculation in some scientific circles, and certainly among many amateur observers, about a possible correlation between heightened solar activity and increased geological activity here on Earth. The intuition behind this idea is quite direct. The sun is the dominant external source of energy for our planet. Logically, when the sun is more active, more energy in various forms reaches Earth. The reasoning follows that if our planet is to respond to any outside influence, it should be the sun. Given that we are near a solar maximum and are witnessing dramatic activity at multiple American hotspots in the same week, one must ask, is it truly impossible that these events are connected? The honest answer is that the existing evidence does not support a strong claim. While some studies have hinted at very weak statistical correlations between solar phenomena and certain types of seismic activity, the results are far from conclusive. Over the decades, a handful of papers have attempted to link sunspot cycles to earthquake frequency or connect the intensity of geomagnetic storms to rates of volcanic eruption. Yet, the findings have been mixed at best. For every study reporting a weak link, another, using different methods on the same data, finds no correlation at all. When these weak connections are reported, they are often small in scale, difficult to replicate, and could easily be statistical artifacts rather than genuine causal links. The scientific picture, taken as a whole, remains inconclusive. There is no smoking gun, no clean signal emerging from the noise. However, the truly significant obstacle for this hypothesis, a point often glossed over in online discussions, is the mechanistic problem. The amount of energy delivered to Earth's surface by even an extreme solar event is orders of magnitude smaller than the energy involved in major volcanic and seismic processes. This isn't a minor difference. It is a vast, almost cosmic mismatch in scale. This fundamental disparity in energy is what gives most scientists pause, and it's a detail worth exploring slowly. Let us consider the energies at play. The kinetic energy released during a hydrothermal explosion at Black Diamond Pool is enormous, capable of launching boulders the size of basketballs through the air with enough force to splinter trees. The energy required to sustain the lava fountaining at Kilauea, spewing molten rock 650 feet into the air for 9 continuous hours, is even more immense. We are talking about millions of tons of rock, heated to over 2,000 degrees Fahrenheit, being propelled against the force of gravity at high velocity. The total energy budget for events like these reaches into frankly astronomical numbers of joules, highlighting the sheer power at work within our planet. This raises the critical question of how such a tiny input of solar energy could possibly trigger such a colossal geological response. We often encounter numbers so vast, with so many zeros, that they begin to lose all meaning to our human intuition. So, what is the actual energy delivered when a major solar event strikes our upper atmosphere? The effects are certainly not trivial. We know that geomagnetic storms can induce powerful currents in long conductors, disrupt satellite operations, and paint the sky with auroras at unusually low latitudes. On rare occasions, they can even damage electrical grids, as famously occurred during the 1989 Quebec blackout. These are real, measurable, and sometimes costly consequences. But the crucial question is whether this energy can influence the planet's geology. The total energy reaching the surface during even an extreme solar storm is many orders of magnitude less than the power involved in building mountains. Much of that incoming solar energy is deflected by our atmosphere and magnetosphere long before it touches the ground. What does penetrate is concentrated in electromagnetic effects, not the kind of raw, mechanical or thermal force that could meaningfully impact processes deep within the Earth. Therefore, even if a correlation appeared to exist, discovering a physical mechanism that could translate such a tiny energy input into a measurable change in volcanic behavior presents a profound scientific challenge. To bridge this gap, you would need some form of leverage, a way for a minuscule external push to unlock a much larger internal release of stored energy. In principle, this is not impossible. Many natural systems are highly sensitive to small triggers when they are already poised near a critical point. An avalanche, for instance, can be set in motion by a single snowflake. Similarly, an earthquake can be triggered by a very small shift in stress if a fault line is already loaded to its breaking point. This trigger model, therefore, is not inherently absurd, but it depends on a very precise set of conditions. It requires the system to be primed and ready to fail on its own. The trigger itself does not provide the immense energy for the event, it simply determines the moment of its release. This theoretical elegance, however, comes with a high burden of proof. That said, in the spirit of fairness to the hypothesis, there are some speculative pathways worth considering. During a solar storm, geomagnetic disturbances induce electrical currents that flow through the ground. These are known as telluric currents, and they are most pronounced in regions with highly conductive subsurface geology. Hydrothermal systems, filled with mineral-rich water, are precisely the kind of environment where such induced currents could readily flow. Theoretically, these currents could have subtle effects. They might slightly alter the behavior of conductive fluids in shallow hydrothermal networks, or perhaps shift the delicate chemistry of mineral precipitation. In an extreme scenario, they could even contribute to the fracturing of silica seals within the subterranean plumbing, which, as we have discussed, is a leading hypothesis for the events at Black Diamond Pool. Exploring these possibilities is part of the scientific process, even if they lie at the very edge of what we can measure. But a single crucial word governs all of these sentences. Theoretically, the amount of energy involved is tiny, and the proposed pathways are entirely speculative. To date, no one has ever demonstrated a clear, causal link between a specific solar event and a specific volcanic or hydrothermal event on Earth. The mechanisms may exist on paper as plausible physics, but the evidence does not yet support the claim that they are a significant driver of geological behavior in the real world. For this reason, the idea remains firmly in the realm of speculation. It is an interesting concept to ponder, and one worth monitoring as we gather more data across multiple solar cycles, but it is not currently supported by strong, empirical evidence. This brings us to a point of caution. If you encounter someone online who confidently claims that recent activity at Yellowstone or Kilauea was caused by solar flares, you should approach that assertion with skepticism. Such a claim goes far beyond what the current data can support. This does not mean the underlying question is wrong to ask. It simply means the answer is not yet known. The absence of a clear answer is not a license to invent one. This entire discussion connects back to a central thread of our journey, acknowledging the profound limits of our current understanding. We do not possess a complete, unified model of how external energy inputs might interact with the Earth's internal geological processes. What we have are approximations, sophisticated models, and rigorous statistical analyses from careful, peer-reviewed studies. What we lack, however, is certainty. There is no grand, unified theory for how our planet responds or fails to respond to influences from beyond its own boundaries. In this landscape, there are gaps. There are areas where data is sparse, where the mechanisms are unclear, and where experts genuinely disagree. And in this absence of certainty, hypotheses naturally proliferate. Some of these ideas are reasonable, grounded in plausible physics, and they make predictions that can be tested. They are open to being revised or discarded based on new evidence. Other hypotheses, however, are not so reasonable. They may invoke mechanisms that violate fundamental physical laws, make claims that are impossible to falsify, and thrive on confirmation bias while ignoring contradictory evidence. At first glance, both types of hypotheses can sound similar, especially when presented with a confident tone by a charismatic voice. The true discipline lies in learning to distinguish one from the other. It is the discipline of being willing to hold a question open, to acknowledge what we do not yet understand, and to resist the temptation to fill that uncomfortable silence with a story simply because it feels complete. Two of America's hotspots are behaving in ways we are still working to interpret. The most honest answer we have is also the simplest. We are watching, we are measuring, and we are trying to figure it out. For now, that process of discovery has to be enough, until the data finally tells us more. Part 18. Are mantle plumes connected? This is a deeper version of the same kind of question, and it requires us to journey somewhere truly remote. I want you to follow me down for a moment, as we are about to leave the familiar surface and visit a place that almost no human conversation ever reaches. For now, let us set aside the sun, the surface coincidences, the weekly news cycle, the social media compilations, and the blinking red dots on digital maps. All of that is noise compared to the question we are about to ask, a question that is older, stranger, and far more fundamental. Could the mantle plumes themselves be connected to one another? Not at the surface, where they appear as entirely separate phenomena, not through the atmosphere, where we know the energy budget simply does not work, but deep below, in a part of our planet that we can barely image and can hardly model. Could there be a true physical link between the ancient roots of these distant hotspots? A genuine scientific concept bears directly on this question, and it represents one of the most astonishing discoveries in geophysics over the last few decades. Deep within the mantle, near the boundary with the Earth's core, geophysicists have identified two enormous structures they call large low shear velocity provinces. The acronym is LLSVP, and once you become aware of it, you will start to notice it in technical papers. Recognizing that you are looking at something genuinely strange about the architecture of our world. Deep within our planet, one of these colossal structures is situated beneath Africa, while another rests under the Pacific Ocean. They are positioned on opposing faces of the globe, nearly antipodal to one another. Their scale is immense, roughly the size of continents, with some analyses suggesting they might be even larger, sprawling across millions of square kilometers of the lowermost mantle. These features rest thousands of kilometers below us. Perched directly above the molten outer core in a region of the Earth we have never directly accessed and likely never will. It raises a profound question. How can we possibly know what lies in a realm we can never visit? The answer comes from a technique known as seismic tomography. When an earthquake occurs, it dispatches seismic waves that travel outward through the planet's interior. The speed of these waves changes depending on the temperature, density, and makeup of the rock they journey through. By recording a single earthquake at hundreds or thousands of stations around the globe, and by analyzing the variations in wave travel times, scientists can construct a three-dimensional image of the Earth's inner structure. It is, in essence, a planetary-scale CT scan, using natural seismic events in place of medical X-rays. When this type of imaging is performed, these features, known as large low shear velocity provinces, or LLSVPs, become strikingly clear. They manifest as regions where seismic shear waves travel significantly more slowly than in the surrounding mantle, a key observation that is captured in their somewhat cumbersome name. Large refers to their continent-like size. Low shear velocity indicates that seismic waves decelerate within them, and province signifies that they are coherent, distinct zones within the deep mantle. Some researchers use a more vivid but less exact name, the African blob and the Pacific blob. Regardless of the terminology, their existence is a verifiable reality. They consistently appear in independent seismic tomography studies conducted by different research teams using various methods. This consistency gives scientists confidence that these are not mere phantoms in the data, but genuine features of our planet's deep interior. The composition of these structures, however, is a subject of intense scientific debate. One school of thought proposes they are simply regions of exceptionally hot mantle, where the high temperatures cause seismic waves to slow down. Another perspective suggests they are chemically distinct from the surrounding mantle. In this view, they could be ancient relics from an early differentiation event in Earth's history, or perhaps even fragments of a Mars-sized object that may have collided with the proto-Earth, an impact that also contributed to the formation of the Moon. A third hypothesis posits that they are accumulations of denser, ancient rock that has gradually settled at the bottom of the mantle over billions of years. Arguments exist for each interpretation, and the ultimate truth may well be a combination of these ideas. It is a humbling reminder that we are still debating the nature of the deepest, oldest, and most foundational structures inside our own planet. And here, the story connects these deep mysteries to events on the surface in a way that is truly thought-provoking. It appears that many of the Earth's major mantle plumes, including the Hawaiian plume, responsible for recent activity at Kilauea, rise from the edges of these LLSVPs. The plumes seem to originate from, or at least be modulated by, the boundaries of these enormous, enigmatic features. Seismic imagery traces hotspots like Hawaii, Iceland, and reunion back to the margins of one of the two LLSVPs. In a very real sense, they are born from these deep mantle blobs. This observation opens up a genuinely tantalizing possibility, one worth pausing to consider. If mantle plumes share their roots in these same deep structures, could there be a shared dynamic that influences their behavior? Could activity in one part of an LLSVP generate pressure waves, thermal pulses, or compositional shifts that propagate through the entire structure, affecting other plumes rooted in the same place? More specifically, could the two American plumes, Hawaii and Yellowstone, share enough of a deep mantle context for a weak, hidden link to exist between them? Could there be, in some faint, complex, and difficult-to-detect manner, a fundamental connection between distant hotspots that spring from a common deep source? The honest answer, and it is important to be clear about this, is that we have no direct evidence for this kind of coupling. The timescales involved in mantle dynamics are typically millions of years. Heat moves very slowly through solid rock, even rock that is plastic, and flowing under immense pressure. Any pressure waves propagating through the lowermost mantle would take days, weeks, or even longer to travel such vast distances, and they would weaken enormously along the way. The standard models of mantle dynamics do not predict the kind of coordinated, week-to-week behavior that would be needed to link distinct surface events at Hawaii and Yellowstone in real time. The dynamics are simply too slow, and the damping effects are too strong. But, and this is a critical caveat, our models of deep mantle behavior are still incomplete. They have advanced significantly in recent decades, but they are not perfect, and we know this. Scientists are still actively debating fundamental questions. How do plumes actually form? Do they rise from a thermal boundary layer? Or are they driven by chemical differences? Or both? How do they maintain their coherence over millions of years while rising through a convecting mantle? What determines their lifespan? And why do some persist for 100 million years while others die out? Why do some plumes seem to wander over time while others remain anchored? These are not settled matters. They are questions at the forefront of geophysical research, with new papers published every year that challenge or revise the existing consensus. Therefore, The possibility that there are connections we have not yet identified cannot be entirely ruled out. It is an idea that simply is not supported by direct evidence at this time. It remains a speculative but powerful reminder of the profound mysteries our own planet still holds. We find ourselves in a position where our current models suggest that rapid connections between distant hotspots are improbable. Yet, we must also acknowledge that these same models have significant gaps in their understanding of our planet's interior. Surprises have emerged from these gaps before, reminding us of how much is still unknown. The recent discovery that Yellowstone's deep plume source is offset from its surface caldera was one such revelation, overturning an assumption that had been foundational in the scientific literature for decades. It is a powerful reminder that more such revisions may lie ahead. In fact, they almost certainly do. This brings us back to the central tension of this entire story. The unresolved questions about the deep Earth are not merely academic exercises. They directly influence how much confidence we can place in our predictions for dynamic systems like Yellowstone and Hawaii. The more we concede that we do not fully grasp the workings of the deep mantle, the more cautious we must be about any sweeping declarations of what is or is not connected. The internet often craves a simple, dramatic explanation, while mainstream thought can prefer a simple, reassuring one. Reality, as it so often does, resides in the complex and challenging middle ground. Skepticism, therefore, must be applied in all directions. It is a point worth emphasizing. We should not reserve our skepticism only for fringe theories. We must also apply it to the mainstream confidence that all systems are independent and well understood. Both extremes represent a form of intellectual complacency. The most honest position, and the one best supported by the current state of the science, is that we are still learning. We are still being surprised. We are still discovering structures inside our own world that we never knew existed. And until we possess a far more complete map of the deep Earth, the only responsible answer to whether these systems are linked is the one scientists are often reluctant to give. We do not yet know. Before we conclude, let us reframe the journey we have taken together over the last hour. With so much ground covered, it is important that the underlying structure of the narrative is clear. Our exploration has carried us from the summit of a Hawaiian volcano to the forested floor of Wyoming. We have descended through tectonic plates, journeyed through the upper and lower mantle, and arrived at mysterious structures resting just above the planet's molten outer core. Along the way, we have touched upon solar cycles, conspiracy theories, the curious psychology of pattern recognition, and the quiet escalation of activity at a thermal pool that was virtually unknown just 2 years ago. My goal now is to draw these threads together, ensuring the shape of the argument is clean and memorable. Because if you walk away from this exploration remembering only one thing, I want it to be the right one. At the heart of this issue is the distinction between two concepts: coincidence and causation. Coincidence is the simultaneous occurrence of two or more events that have no causal link between them. Causation, on the other hand, is when one event is the direct result of another. Confusing these two categories is the source of most flawed reasoning about the kinds of events we have been discussing. In fact, much of human reasoning stumbles at this very point. We observe two things happening in close succession, and our brains, which evolved to find connections in our environment, immediately attempt to forge a link. This link can feel real, even obvious, like an insight that others must be missing. But a feeling is not evidence. The strength of a perceived connection in our minds tells us almost nothing about whether that connection truly exists in the physical world. The fountain of lava at Kilauea on the 5th of May, 2026, and the explosions at Black Diamond Pool a week prior are coincidental in time. They occurred within roughly the same news cycle, and that is the only sense in which they are connected. They are not causally linked. No reasonable model of Earth's dynamics can forge a mechanism by which one of these events triggered the other. The systems are simply too far apart, their subterranean plumbing is too disconnected, and there is no plausible way for the energies involved to transfer from one to the other on the timescales we are observing. If a meteor had struck the Atlantic Ocean during that same week, we would also call it a coincidence. If a volcano in Indonesia had erupted on the same day, that too would be coincidental. The world is filled with large, energetic events that happen close together in time, none of them causing the others. The week of the 5th of May, 2026, was just one example among countless others. But there is a more useful framework for understanding this, and it is the one I hope you will take with you. The Earth is a continuously active system. At any given moment, dozens of volcanic systems are in a state of eruption somewhere on the planet. This includes volcanoes like Stromboli in Italy, Sakurajima in Japan, Sangay in Ecuador, as well as Reventador, Semeru, and Erta Ale. The list is long, and most of these eruptions never make international news. At the same time, hundreds of active geothermal systems are quietly bubbling, steaming, and occasionally exploding across the world's volcanic arcs and rift zones. Every day, thousands of small earthquakes occur, most of them too faint to be felt, their existence registered only by the global seismic network and logged in databases that few people ever see. The Earth is never truly quiet. Our planet is never still. It is, at every moment, a noisy, dynamic, and energetic system, constantly releasing energy through hundreds of channels at hundreds of locations all at once. So, when we declare that the Earth is unusually active in a given week, what we often mean is that we notice times more events than usual. This is frequently because the events happened in places that command our attention. The Earth itself was likely just as active as it always is. We simply turned our heads. We received a notification on our phones. We opened a news app at the very moment an algorithm decided that a particular cluster of events was worth showing us. The activity itself was not new. Our attention to it was. Once you grasp this fundamental distinction, you begin to see how much of the global awakening narrative falls apart on its own. The Earth is not waking up. The Earth has always been awake. We are the ones who only notice it from time to time. What we observed during the first week of May 2026 was largely an artifact of attention. The American hotspots garnered focus precisely because they are American hotspots. They have famous names. The news media covers them. Hawaii has tourist webcams pointed at its lava flows, and Yellowstone has news bureaus that report on every park advisory. Other simultaneous events occurring around the planet, which were equally significant in their own geological contexts, simply did not receive the same level of global coverage. There were earthquakes reported in places that rarely capture headlines, and volcanic events that occurred in regions without dedicated press offices. Thermal anomalies flickered in countries whose monitoring data does not easily find its way into English-language news. While all of these events were entirely real, none received the same focused attention as the incidents at episode 46 or Black Diamond Pool. This reveals a crucial truth. The pattern we often perceive is partly a reflection of the data itself, but also largely a reflection of where we choose to direct our gaze. The signal we think we are detecting is often just the shape of our own attention mirrored back at us. However, it is vital to recognize that the comparison between Hawaii and Yellowstone is not a product of this same attentional bias. Their connection is real and deeply informative. This is not a mere coincidence, unlike a random global cluster of seismic activity. Instead, we are observing two major American mantle plumes, both creating surface phenomena that we can study in remarkable detail. We have not chosen these two systems arbitrarily. We study them together because they are rooted in the same powerful deep earth processes. Both originate as immense columns of buoyant, hot rock rising from far beneath the crust. Both pierce the tectonic plates from below, generating volcanism in places where conventional plate boundary theory suggests none should exist. When we compare them, we are not comparing dissimilar objects. We are examining two distinct examples from the same rare geological category, and it is in their differences that we can find the most valuable lessons. The contrast in their behavior is striking. Hawaii's volcanic system is stable, predictable, and episodic. Pressure gradually builds. A fountain of lava erupts. The pressure is released, and the system pauses before repeating the cycle. This cadence has been remarkably consistent for more than a year, and its output remains contained. By every available metric, the system is functioning exactly as expected. Yellowstone, on the other hand, specifically at the level of Black Diamond Pool, is becoming less stable and less predictable, with its individual events growing more dramatic. Its escalation curve is sharp. After 152 years of complete inactivity, it has experienced 3 significant explosions in less than 2 years. The 2 most recent of these occurred within a single 2-4-hour period. This contrast is not random noise. It is a clear signal, representing a real and meaningful difference between 2 systems that share a common, deep origin. That difference is telling us something profound. The signal reveals a fundamental truth about planetary geology. Mantle plume systems can produce wildly different surface behaviors, depending entirely on local conditions. The very same kind of deep engine, when filtered through different crustal and hydrothermal networks, can manifest as gentle fountains in one place and violent explosions in another. The plume itself sets the energy budget. It dictates the amount of heat delivered, the volume of magma produced, and the total energy available. But the surface expression, which is what we actually see and experience, is shaped by the architecture above that engine. The crust, the plumbing of conduits and fissures, the presence of aquifers, the network of faults, and the chemistry of the local rock all act as filters. These factors process the deep signal in unique ways, leading to dramatically different outcomes from the same underlying process. The variability is not at the level of the engine, but at the level of the filter. This very concept is why the situation at Yellowstone feels so unsettling, and why the activity in Hawaii is so reassuring. Both are mantle plumes, sharing a genesis in the same deep earth dynamics. But the surface filter at Yellowstone is now doing something that the filter in Hawaii is not, and we do not yet have a complete explanation for why. This is the true pattern emerging from beneath the noise. The story is not that the Earth is waking up, nor is it that the sun is causing eruptions. It is not about a secret synchronization coordinating distant hotspots through some hidden channel yet to be detected. The real pattern is more local, more specific, and in some ways more disturbing. It is the observation that 2 of this continent's most important volcanic systems possess very different surface filters, and one of those filters is currently behaving in a way we cannot fully explain. The deeper signals remain quiet, yet the shallow behavior is actively changing. This mismatch between what we expect and what we are observing constitutes the actual mystery here. It is a mystery that resides not in the profound depths of the mantle, but in the tangled, difficult-to-image plumbing of a single thermal pool in northwestern Wyoming. That is the essential story. That is the thought that should remain long after the dramatic narratives fade. The focus should not be on a global awakening, nor on speculation about solar storms or hidden mantle connections. The thing to remember is the gap between what our models suggest should be happening and what the ground is actually doing. It is within that gap that the real questions reside. That is the gap we are watching, and for now, it is not closing. So, our journey ends where it began, at Black Diamond Pool. This is a small, deep, dark blue thermal feature nestled within Biscuit Basin, in a forest in northwestern Wyoming. For 152 years, this pool did nothing dramatic at all. Yet, since 2024, it has been the site of 3 major hydrothermal explosions. The two most recent events happened within 24 hours of each other, with the second blast being larger than the first. We do not know precisely why. Scientists have theories, with the plumbing model being the leading explanation. This model suggests that the slow deposition of silica over many decades gradually narrowed the underground conduits. This constriction allowed pressure to build over time. The seal first failed in 2024, releasing some of that trapped pressure. A second seal failure in late April 2026 produced the first of the recent explosions, which in turn cleared a pathway for a deeper, more pressurized reservoir of water to follow just hours later, causing the larger second event. This hypothesis is consistent with the available evidence, but other possibilities remain, and the data is not yet rich enough to make a definitive conclusion. What we do know with confidence is that the deep Yellowstone system is not the driver of these events. The vast magma chamber is not pressurizing, the ground is not deforming in alarming ways, and the seismic networks are not detecting anomalous patterns. This means that whatever is happening at Black Diamond Pool is a shallow phenomenon. It is occurring in a tangled, poorly imaged region of the subsurface that we have very few tools to observe directly. This is the part of the story that should stay with you. Here in the United States, we have two of the most intensely monitored volcanic systems on Earth, and yet there are still fundamental processes happening just beneath the surface that remain a profound mystery. At Yellowstone and Kilauea, we have deployed our most sophisticated monitoring tools, a world-class network of seismometers, GPS receivers, gas sensors, and satellite radar. Decades of research have been dedicated to these geological wonders, forming the basis of entire scientific careers. Yet, for all our expertise, a single, small, thermal pool that begins to act in ways our models cannot predict leaves us without a certain answer. This is a moment of profound and concrete humility. It reveals that even with the most intensely studied geological systems on Earth, significant gaps remain in our comprehension. And what makes this so striking is that these gaps are not found at the distant frontiers of our knowledge, but right in the center of what we believed was already understood. This sense of humility extends directly to the larger puzzle of mantle plumes. For generations, scientists have mapped, modeled, and documented the plumes beneath Hawaii and Yellowstone, considering them the most thoroughly examined on the planet. But a recent discovery has challenged our core assumptions. We now know the deep source of the Yellowstone plume is not directly aligned with the surface caldera, a finding which suggests that the fundamental geometry of these systems was misunderstood until very recently. This raises a critical question. If our understanding of something as basic as the plume's shape was incomplete, what other fundamental aspects of their nature might we have also misinterpreted? The list of what we do not know seems to be growing. Let us pull back our focus to a continental scale. The United States holds a unique position on our world, as the only nation with two confirmed active mantle plumes situated beneath its land. These are two rare and ancient engines of geological change, driving forces from deep within the Earth. Each is capable of generating phenomena on the surface that range from breathtaking fountains of lava to cataclysmic eruptions of steam and water. Their origins are rooted in processes that may begin near the boundary of the molten outer core and the solid mantle, some 1,800 miles beneath our feet. Each plume is part of a narrative that has been developing for tens of millions of years, and this story will continue for many millions more. We are constantly observing, monitoring, and studying these powerful systems. Imagine a scenario unfolding in the first week of May 2026, where both plumes exhibit significant surface activity at nearly the same time. One of these events proceeds exactly as our models and expectations predict. The other, however, does something entirely unforeseen, something we are unable to fully explain. It is precisely in this space, the gap between what we anticipate and what we actually witness, that the true story of discovery resides. Ultimately, this reminds us that we inhabit the surface of a world whose interior remains largely unmapped. The very continents on which we live are adrift upon a layer of slowly churning rock that is forever hidden from our direct view. The hotspots are the deepest expressions of this inner world, occasionally reaching through the crust to remind us of their presence. They offer no warnings, they do not coordinate their actions, and they make no announcements. They simply act. When these moments occur, our only recourse is to watch, to strive for understanding, and to concede, with the honesty that science demands, that there are forces at work beneath our feet whose language we have not yet deciphered. We find ourselves watching two immense geological systems that we do not completely comprehend, both active on the same continent. Their story is far from over. They are not finished speaking. The next time one of them stirs, the real question is not whether we will be able to hear it,